20 years. Like she's very in the field. She's like, it's like we have another faculty like Vivek Srikumar works between machine learning and NLP, and she works like in NLP.
Okay.
And so it's very good. You could take that and ML in this course, and there'd be, there's fairly little overlap, and they're all kind of data analysis. This one's very specifically focused on the NLP aspects. So there'd probably be a little bit of like doing K-grams and stuff, but then I think it's going to get much more into kind of the actual, a sentence as these components, and you can like learn all these components, and that's what's necessary to get a much deeper understanding of the context.
So I emailed her to find out.
Yeah,
I haven't heard back from her.
Okay.
Would you probably be able to, if you see her?
Yeah. Yeah, I'll
definitely like that.
Next time I see her, I've been chatting with her a bunch the last couple of days, and so I don't. Next time I see her, I don't like. I don't even see her necessarily every week, but I've seen her a bunch.
Sure, I figure she'll probably get back to me. Relatively soon.
Okay.
I'm just thinking if she doesn't, I would also like to know, like, you're mainly done in Python. If not, what would I need to know, and do I have to start
need to get started on here. Okay, great. So let's get started. So thank you for being inside the lecture on this on this nice warm spring day. Hopefully people don't realize all of a sudden and leave for the exits. So I saw you thinking, but you're sitting on the inside of the row, so I think I'm just a little bit safe. So let's see. So here, so we are in one of the last sections of like the dimensionality reduction part of the class. I might add some into the next lecture because I stole some from there earlier. So we'll see, but we're going to kind of be talking about essentially some uses of PCA within other approaches, and specifically some kind of nagging issues that I think I mentioned to a lot of you in your feedback in your me report that we would be talking about something this week that would hopefully be helpful. So hopefully we'll cover that in lecture today. And then the regression homework was due today, and then the dimensional reduction homework is posted. I think that one should be even simpler than the regression homework. I guess regression, the second question probably may have been confusing, and then hopefully once you got it, it was not too hard. Once you figure out what it was asking. And then there'll be only one more homework left, graphs, which will be due after the end of the semester. I've kind of pushed that off so you can kind of focus on the other aspects of class. This will be, I'll probably post this around Wednesday the 10th, April 10th. Okay, so great. And I have the exams, the midterm exams up here in class today. Probably the last day I will bring those in to class, and otherwise I'll have them in my office. You can come in office hours. You can come up after class in order to get them. So okay, so we're going to be talking about metric learning, and the basic kind of, I'll talk about kind of three somewhat related algorithms, which will get kind of progressively more and more so complex, and solving slightly different goals. But the starting point is, so students often will have you often start with some data, which will be in n times d. So this is, it means you think of, you have so you have these n data points, which are each in d-dimensional space, but this could kind of be the start, but they may not have like all the same units, right? So it could be that xi is going to be something like the height, the weight, the age, the income, you know, so it's something like this where you're mixing units together and you'd like to do something like dimensionality reduction to draw a picture, or you'd like to do like a regularized version of regression. So you kind of need to put a norm on these data points, and I don't know how to mix these coordinates together. How do I learn the right ratio between the distance between the height coordinate and the weight coordinate, or the age coordinate, and something like that, right? So this is a fairly common issue that comes up, and so I wanted to give some insight into how to approach this. Okay, and so this is generally the goal, and the third algorithm I will talk about will be trying to directly address this problem. All right, but the first two are going to kind of work on slightly easier problems, and in all of these, I'm actually going to have some sort of input, and it's going to have these objects A1 up to AN, and I somehow want to create some, and it's always going to be some sort of linear map, or I would say not necessarily linear map, but kind of a linear conversion where I'm going to take each AI and map it into some space, which is an RK. And then it's going to make sense that the distance, that a useful distance between AI and AJ is going to be exactly this mapping, AI. So it's going to be exactly the Euclidean distance. And not only is it Euclidean distance, but I'm going to have a k-dimensional vector, right? So it's going to be some nice kind of, I'm going to have a vector representation of these objects. And it's going to be k dimensions. I could set, so notably, if I set k equals 2, then I can draw a picture, right? So if I set this to a 2-dimensional Euclidean space, I can draw a picture, right? And then I can use the Euclidean distance, and I want to be able to use the Euclidean distance, and with properly kind of normalized weights on the coefficients. So then I can do something like a regularization or regression where I put a norm on these things, and that makes sense. I can draw a picture by going down to 2 dimensions. I can run Lloyd's algorithm for a k-means clustering because I'm in Euclidean distance, right? So it doesn't need to be 2 dimensions for that, right? But now I have a natural Euclidean metric. I can take the average of things, right? So I have these nice things happen. If you want to do classification, you can then do a linear classifier, would hopefully make sense, right, in this space. So we don't talk about that so much in this course, but that would also make sense. So you're kind of mapping into a subspace you hopefully is useful. Okay? So I somehow want to take data. I may not initially have d-dimensional coordinates. I might. Okay? So so I'll start with the first kind of, the first algorithm is going to be called, and in each of these I'm going to give one algorithm for a class of algorithms that I think is kind of the simplest, most natural, maybe not even the best, but kind of at least something I can explain all 3 of them inside of the lecture. So the first approach is called multidimensional scaling. I don't really know where this name came from. It's pretty ancient, right? So I don't know why it's called multidimensional scaling or what these are referring to. It has to do with multiple dimensions, so people just call this MDS, and this is kind of used. There are versions of this, and this is sometimes called classical MDS, or just if they just say MDS, they're probably talking about this algorithm. Okay, and so the input here is going to be one of two options. Either one is going to be an n by n distance so matrix, so that it'd be a D such that Dij is equal to some underlying distance between some object AI and Aj. Okay, the other option would be just a function. So I just have access to a function, like I can run a piece of code and it outputs some number. So it's a bivariate function between AI and Aj, and this is going to output the distance between AI and Aj. Okay, so think of this. This could be something like I have cities. I want to kind of know something about some inherent distance between them, and I can query like some website that gives me the cost in dollars of flying on an airplane in between these two cities, right? I can ask for the cost of a flight between the two cities, and that will give me a number, and I could use that as a distance. Okay, so you know, it could be I have like function access to some distance function, right? That's not, so I don't necessarily have representation in some space where I can measure the distance, but I can ask a website, or I can run some other algorithm and output some number, which is my distance. Okay, or maybe I've done that and I've gotten the full n by n distance matrix pre-recorded. So we're going to actually work with this distance matrix. So assume that I've run this query for all pairs of points. Okay, and then I would get this distance matrix out of here. Okay, there are other algorithms that don't use all of the n by n, so because they want to be more efficient, they don't want to look at an n squared kind of cost to do this, so they can work with just this function. The classical MDS works with this full distance matrix here. So we're going to, you know, for classical MDS. Okay, and so again, the goal here, as I mentioned, is some embedding of xi, xj, let's just say x1, x2, xn in some rk, such that for all xi, xj, that d of ai, aj is going to be, or I should say lowercase d for consistency, di aj is approximately equal to xi minus xj. Okay, so I want to find actual vectors, k-dimensional vectors, so that the Euclidean distance between those vectors is approximately the distance from the distance matrix so I'm given. If the original distance matrix corresponds with some Euclidean distance, okay, if it was derived from an actual Euclidean distance, then I can say something meaningful about how close this is going to be and how this is actually the optimal thing to do in like an L2 sense. But otherwise, I can't necessarily make claims about how optimal this is. There are other ways that you can kind of argue about some different optimal approach. This classical MDS kind of, in these cases, is kind of just a heuristic, and hopefully it works. And in general, it works pretty well. Okay, so I want these distances to be about the same. Okay, and I need to find this embedding. So I'm not originally given the locations in some like n-dimensional space or something like that, or some high-dimensional space. I'm just given the distances. How do I get this embedding that preserves these distances? Okay, so the basic insight, the main insight into how this works is that I'm going to assume, basically assume that d a j is going to be so derived from Euclidean. So there's some Euclidean distance underlying this, some L2 distance, which is giving me these distance values. If that's the case, then I can write AI minus AJ, right? So that there were these data points that did have a natural Euclidean distance in some maybe very high dimensional space, which I can decompose the squared distance so it looks like this. Right? So this is just a property of squared distance. I can write it by kind of AI norm squared plus AJ norm squared minus 2 times the inner product. Okay. And this means that what's more useful is that AI AJ, I can write this as 1/2 of minus AI squared minus AJ norm squared. Right? So I can derive, if I know these norm values, I can derive this inner product. Okay? So why is this inner product useful? Because I want to somehow use my tools from PCA and SVD and eigendecomposition in order to get a low-dimensional subspace, right? So these are the tools we have. And if I knew, so if I kind of know some matrix A, right, which is R times N times D, right? So there is some Euclidean embedding of this matrix. Then then I can think of this matrix A transpose, which is a square matrix. Okay? And I'm going to call this M. Okay? This square matrix, I can then say the eigs of M, right? So the eigenvectors of the square matrix is going to give me, the top k of them is going to give me a k-dimensional embedding, right? So I'm going to write this as U, I'll make sure my U's and V's are different, U, V, U transpose, right? This is an eigen decomposition, and if I say, and then U, K is essentially going to be an n by k. So an n by k dimensional matrix, which is kind of the first k eigenvectors of A, or of M, the first k eigenvectors of M, which are the first k left singular vectors of A, which gives me the optimal L2 embedding into a k-dimensional space. Okay, so if I know A, I can basically think of computing this outer product matrix and do the eigendecomposition and get this embedding, right? So this is the answer, right? So if I can get here, then this is my answer. This kind of tells me what the right embedding is. So how do I get this M? Well, if I look at what Mij is, Mij, this ij element of the matrix, this is actually equal to the inner product between Ai and Aj. Okay, if you unroll what this matrix multiplication of A transpose is doing, the ijth entry of this matrix M is actually this inner product. But if you went back here, I almost have the inner product, right, in this derivation, and it's using this squared distance here. Okay, so what I want to do is I want to set this equal to 1/2 of AI aj squared, and this is actually just dij squared minus ai squared minus aj squared. Okay, so now I can derive this inner product for all pairs of these vectors. Yeah.
Is that off by a negative sign, or does that not matter? Going back to the other slide.
Yeah, possible, but yeah, it looks like I'm off by minus sign. Yep, good. So
I didn't know if it was
yep.
actually important.
Yeah, no, it's yeah. Otherwise, you'd have all these negative terms in there, which would be bad. Yep, good. So I have actually this. Okay, probably better to write them in the other way, but okay. So now it's correct. So thank you for fixing that. Yeah, I guess it's right in the notes. So okay. So still, I have this first term here. I've got this first term, and this is directly from the squared element in the distance matrix. But I don't have these two terms. I don't have the norm of AI or the norm of AJ. Okay, so if I can get those, then I can derive the inner product of every AI and AJ, create this MIJ matrix, and do the eigendecomposition and take the top k eigenvectors. And that's my embedding. Okay, so all we need to do is solve for these guys here. Okay, so the insight into how to do this is that when I'm taking this data, which doesn't have any coordinates, and I'm putting it in some space, it's going to be shift invariant. If I add 2 to the first coordinate of everything, it doesn't change the norms, because every distance is then going to be a subtraction of 2 vectors, and that gets subtracted. So I can add anything to these coordinates. I've got this extra freedom in how to do the embedding, right? So this UK or this you know, my Euclidean embedding is going to be shift invariant. So I can set where the origin is. I can decide what's the origin, which means, so what I'm going to do is I'm going to set so that x1 is going to be the origin. So I can choose one of the points to be the origin. Okay, if this is true, that means this implies that x1 is going to be 0. The norm of x1 is 0. Okay, it also implies then that AI minus x1 minus a1, actually this can be a1, sorry. Okay, a1 is 0, so AI minus a1 squared is going to be equivalent to AI squared. Okay, so that means that this is then going to be di1 squared, which means that this is going to be di1 squared, and this is going to be dij, or dj1 squared. It should be symmetric. Okay, so I could do d1j squared or dj1 squared either way. But now I can also read these off the distance matrix. So I calculate those, I solve for all the inner products, and I do the eigendecomposition, and I get my answer, which is the embedding. All right, so this is the classical MDS algorithm. Right? I solve for these off the distance matrix, calculate all the inner products. I do that n squared times, then I do an eigendecomposition, and I get k-dimensional embedding. Okay, so now if you just have distances but not an embedding, say, for instance, I have data sets and I have the Jacquard distance between them. Right? I can go and do this for the Jacquard distance, and I now can embed it in two-dimensional space and draw a picture, which is in some ways roughly the best way to draw a two-dimensional picture based on Jacquard distance. Okay. So great. So this is the first algorithm. Okay. So if I just know the distances, but not embedding, this is how I create a Euclidean embedding. Okay, let's move on to the next algorithm. So this is going to be called linear discriminant so linear discriminant so analysis, and sometimes just called LDA. There are other algorithms in similar spaces also called LDA, but there's like latent Dirichlet analysis, which is something different. Okay, so don't confuse those two things. That also kind of gets you an embedding in some Euclidean space, but with a very different kind of setup. Or not too different actually, but these are not the same thing. Okay, so the input to this, again, the goal is going to be a representation in a k-dimensional Euclidean space, but the goal is going to be slightly different here. So now my input is going to be some set X, which is going to be R and D. And I'm actually going to assume that the distance between xi, xj actually makes sense to use xi minus xj squared. So I'm going to assume actually now that the Euclidean distance makes sense on these vectors. It's in d dimensions, which is going to be larger than k, right? And so k is going to be less than d. Okay, but I'm going to add something else on here. I'm also going to say that I have these clusters, S1, S2, up to Sk. K might not be the same as, let me use a different variable here. So SL. Okay, so I've got these clusters which are going to be subsets of X, and S, it's going to be disjoint that these are going to be disjoint, and the union over all SI is equal to X, right? So this is a partitioning of the space. Okay, so I've got clusters, and now I want to find the best k-dimensional subspace that separates the clusters. So I want to draw a picture that shows the clusters well, but I'm going to restrict that it's a linear subspace. Okay, so there's a variety of algorithms that have come out, and some are very popular. There's one that's called TSNE, which is extremely popular, that has a similar goal here, to draw kind of usually two-dimensional pictures that shows clustering results. And it similarly tries to show the clusters well. This one does not guarantee that it's a linear subspace, and it's somehow distorting the distances. It's assuming that it's trying to do something like preserve the Kale divergence or something related to this instead. Personally, I'm not a big fan of TSNE because it's kind of distorting what's going on in some way to show you pictures which might be better than is actually possible. Whereas this will actually show you some linear subspace. So it's some way of projecting the data so that it tries to show these clusters. Okay. Okay, so how do I find this linear subspace that kind of shows these clusters? Okay, so I'm going to need some notation here. Let's say mu is going to be, or let's first is going to be 1 over the size of x. So this is going to be the mean of all of the data points. right? So I start Euclidean distance, I can take means. This is the overall mean. And I'm also going to say mu I is going to be 1 over SI. Right, so this is the mean of the cluster I. Right, so I'm going to have mean of overall and the mean of the cluster I. Okay, and I'm also going to define the covariance for the cluster I. So this is mean. This is the covariance, which is going to be 1 over SI. And now I'm going to take the outer product. Right, so this is going to be an R d by d. So this is going to give me a d by d matrix, which is, think of, I've centered all the data points, right? So then I'm kind of like doing, this would kind of corresponds with doing PCA of the data points, but I've kept all the d principal components here. So if you haven't heard of covariance before, that's one way how to think about this. Okay, and so then I'm going to find two general quantities. First one is the between class covariance, which I'll call sigma b for the between class, which is 1 over x. I equal 1 to L, so over all the different classes. And then I'm going to calculate okay, so now I've taken outer product, but I'm just looking at the means of the individual classes versus the overall mean. That's what's going on here. So this is how the separation between the classes. So I'm representing each class, each cluster, by its center, and saying how are these distributed. Give me that covariance matrix. That's sigma b, the between class covariance. And so then I'm going to also have the within class covariance, which is sigma w, and x, make sure I write this up right, I equals 1 to L okay, so now I'm taking the covariance matrices between the classes, and I want, and I'm weighting them by the size of the class. So the larger the class, the more this matters. Same is going on here. Right, so in both cases, I'm adding together effectively, if there are n data points, I'm normalizing by 1 over n, and I'm adding together L terms, but each weighted by something that adds up to n, right? So this makes sense. Similar, normalizing by 1 over n, adding over these L terms, but weighting them by the number of points in that class. I could expand this out as well, right? By just plugging in the definition from up here. You'll see that there are n terms again. So, okay, so I've got these. So basically, if I'm going to project this down, so I show the classes, the clusters well, I want this term to be large. I want the difference between the central overall mean and the mean of each cluster to be large, those to be well separated. But this one I can have small. This is everything else that's going on. This is what's going on inside the clusters. I can have those be well concentrated. I want to show those on top of each other. This term, once I've factored out these dimensions which make this large, this one is probably the noise term, right? So if you're thinking like just doing PCA in the data, I want the directions which capture a lot of variance in the data, but not the ones going off that subspace. And this is saying a little bit more specific in that I know these clusters have already been assigned, and I want to show them well. So not just all the variance, but the variance that shows the clusters. So that kind of, if I know these clusters, then this is probably the dimensions which actually separates my data in a way that's useful here. Okay? So once I have these terms, so I want to find, basically my goal is to find vectors u which so maximize u transpose sigma b, right? So I want directions so that the between class covariance is large and the within class covariance is small. So I want directions u, and I want to find a basis of k of these, which make this term large. Okay, hopefully that kind of makes sense of what's going on. The between class, I'm spreading out the cluster centers, but the data within the clusters, I can make those small. And this is what I want to weigh here. And so now I want to find a set u1 up to uk where k is less than, I think it needs to be less than L minus 1 for this to work. Right? L different clusters to start with. Okay, and so it turns out that the answer is going to be the top k eigen vectors of, so drum roll, okay, of this matrix, this D by D matrix. Okay, so I took the between class covariance. I want eigenvectors where directions along that are large, right? And the inverse of the within class covariance. I want directions along that to be small, so I take the inverse, right? When I'm dividing by something like a matrix, the natural thing to do is to take the inverse and multiply by it, because I can't divide by a matrix, but I can do this. Okay, and so it turns out that taking the top k eigenvectors of this gives me the right answer, gives me the best answer. All right, so this is, again, once you have the clusters, you can compute these quantities, which are all really simple to do. They give you these D by D matrices. And I multiply together one by its inverse, and I take the top k eigenvectors, and this gives me my embedding. So this is the LDA algorithm. Yeah, so the input here are the clusters, right? So let's say I've given clusters of a high dimensional space, like let's say I use Jacquard distance and I create clusters using spectral clustering, or I could use anything, right? It could be a hierarchical agglomerative clustering in Jacquard distance. And then I could try and do, like, I have distance, I could do an MDS embedding. But that might not be the right distance to really show off the clusters well. That might mean it's not the most important subset of directions I want to see. And this one will do better. And this is just as reasonable to do, assuming that you know these are the right clusters.
So at the beginning you mentioned that it only works with disjunct sets, which means the clusters which are not each other, right? But
yeah, so for hard clustering.
So you might see clusters that are actually like crossing each other, but then maybe on three-dimensional plane they're not, right?
Yeah.
The more dimensions we have, the better understanding if they actually do cross.
So if I have clusters like this, then the magic, I turn them like this, and now I can see them, right? So you have to, you're getting this high dimensional stuff going on. So especially if you're doing single link clustering on data, because it's all touching each other, right? It's in 3 dimensions. I don't see what's going on, but if I find another subspace, then it actually shows me what's going on here, right? And that's what I want to do.
And so the question becomes, given arbitrary many dimensions, we don't have any clusters that cross each other, right? We can find the way where the clusters are actually.
Yeah. Once you get in high enough dimensions, you can always usually find these nice linear separators. Yeah. I guess, wait, to do this, I need to first get them into Euclidean space to take means and stuff, right? So what I said about Jacquard distance maybe doesn't work by itself. I would need to do MDS first. But I could do MDS up to like the full n-dimensional space, and then I could run this, for instance. Might be the right thing to do. Okay, good. So this one was also fairly easy. A little bit trickier. I needed to compute these different quantities, but kind of procedurally, it's pretty simple, and hopefully, intuitively, it's making sense why this should work, right? I want this to be large. This is the covariance between the centers, and this to be small. This is kind of the deviation within a cluster itself. And so I want like that quantity to be large, one over the other, so I just take the inverse of one of the matrices, and that tells me what to optimize. That's great. Yeah?
I was just curious, is there any intuition on whether, maybe you kind of address this a little bit in terms of getting your distances in Euclidean first, but like using PCA first and then clustering versus like clustering and then using LDA?
Sure, right. So, yeah, so like if you're using like a k-means clustering on original Euclidean data, it's probably going to implicitly be kind of, you probably just want to take the subspace through the clusters, this start with, this actually, through the cluster centers, they're probably optimizing roughly the same thing. K-means and PCA are probably roughly going to give you something similar to what LDA is doing. If the clusters are defined in a way that is not based on the original Euclidean distance, then this will probably help more. Now, it's not always going to be true, right? There could be some deviation, and this might do a little bit better. There's another interesting point that you raised that I don't think I've mentioned in the actual lectures this semester so far, but combine together clustering, specifically k-means clustering, and so dimensionality so reduction, it turns out that both of them help with the other. Okay, so basically there are results from like, for instance, from the random projections that say really the number of dimensions you need is not this 1 over epsilon squared log n, but 1 over epsilon squared log k, where k is the number of tightly connected clusters. It really only depends on the cluster centers. If you preserve those well, you probably preserve everything else fairly well. On the other hand, it's shown that if you want to do clustering, and for instance on k-means in very high dimensional space, it's actually helpful to do PCA or random projections first. For one, it's going to reduce the dimensionality, and it turns out it preserves most of the properties you need for k-means, so you can actually do fairly well. There's been some research on how low can you project it while still preserving these things, but it turns out, you know, it's basically preserving the right properties. And so one is it reduces the runtime if the dimensions were super, super high to start with. The other thing is it might actually be actually more robust to do dimensional reduction before k-means clustering, because hopefully you think of the actual subspace you care about is what's the span of the cluster centers. And everything coming off that is probably like full dimensional noise just based on measurement error in the data. Okay, and so by reducing the dimensionality, you're probably, if these clusters are separated, they're going to have high variance, and you're probably going to find that subspace and get rid of these noise components. And then sometimes the noise components will dominate the other stuff or obscure some of the other signal going on. So if you can pre-process and get rid of some of that noise, then that will help. And so there's some statistical reasons why this works slightly better as well. So it's actually, if you're doing k-means clustering, then these make sense to mix. K-means is nicely has to do with like the L2 metric, the same as PCA. Dimensionality reduction with using random projections preserves most kind of distances that have to do with Euclidean distance as the base measure you're doing. So it's if you're looking for a really efficient first pass over the data, doing even like a count sketch or a JL might be good before running a very massive clustering algorithm. Yeah, so these are related, and of course, spectral clustering defined with Euclidean dot product is actually doing both of these things at the same time. If you want to kind of think about that a little bit. Okay.
So it's a better strategy to run PCA before you actually run clustering.
If your dimensions are like super high, like super high, then yeah, that probably makes sense to do. I wouldn't try and go down all the way to K if I want to find K clusters. I'd go down larger. I'd stay larger than that by, say, a factor of at least 10. Right? But if you're starting with a million dimensions and you want to find 10 clusters, you're probably safe to go down to 100 dimensions first. I would say that makes sense. It would also, and should also, the dimensional reduction you can actually do faster in one pass, and then you can make multiple passes on whatever clustering algorithm, and it'd be faster because the dimensionality is lower. So every time I compute a distance, I don't need a 1,000,000 dimensional vector, I need a 100 dimensional vector. And those will be faster.
And there's a way to choose the optimal amount of dimensions to reduce it.
Yeah, there's like theory about what the right number is, and that might be 10 times k. Sometimes in statistical settings, the right number is 3. You know, like there's a lot of time series analysis where really doing PCA down to 3 dimensions is often the best trade-off between kind of the best, like, gets rid of a lot of noise while preserving enough of the signal. You know, that's not always going to work, but there are multiple answers to this sort of question. And it's going to depend on your data and what you're trying to do with the analysis, what the right dimensionality they should go down to. So good. Okay, so now we're going to talk about the third algorithm. This is this one I'll call distance metric so learning. Okay, and so this is the original problem I talked about. You have data. Maybe it's Euclidean data. So the input here is going to be x, which is going to be an element of n times d. So n-dimensional data. I can treat it maybe as Euclidean, but I don't trust the weight on the vectors here. So what I would like to do is to define a Mahalanobis so distance. And so that's going to look like between 2 points P and Q is going to be defined as P minus Q transpose M P minus Q square root. And this is where PQ is in RD and M is in RD times D. So M, let me write M a little better here. M is going to define this distance. It's going to be a D by D matrix. If this was the identity matrix, this is exactly the Euclidean distance. Okay, and if I keep M as, so if M equals I, then this is Euclidean. If M equals M11, M22, MDD, right? So if this is going to be a diagonal matrix, what I'm doing is these are weights on this is basically a weight on the second on like the second coordinate. So if I force M to be a diagonal matrix, it's telling me basically a weight on, you know, the second one, the second entry on the diagonal is the weight on the second coordinate. How important is that coordinate, is what this is telling me. But in general, M could be d by d instead. And what that's doing is instead the general case is that I'm going to have, remember all these pictures I've drawn, you know, I'm going to have this d-dimensional space, and now this matrix M is going to be some sort of ellipse in the space. Right, so I can think of the singular value decomposition of this, and these are like the right singular vectors is going to define the, or I guess the eigenvectors of the square matrix. The eigenvectors are going to describe the axes of this ellipse, and I'm skewing the data in this way. Right, so this is going to say that the, this would say if M22 is large, then the second coordinate is going to be, I'm going to multiply that by a large number before I add it up into the sum. Right, now I can say that I'm going to skew it in some other way that's not just according to the coordinates. So it could be that two coordinates, if either of them is large, it's going to be large. But I kind of want to weight them jointly in some way. So I don't need to weight them individually. I can have this joint kind of weighting between them. And that's what this kind of this general m-dimensional, m d by d dimensional matrix is giving me. Okay, so this is the general form of the Mahalanobis distance. And so my goal is to learn a Mahalanobis distance, which I can actually do, I could create, if I wanted to, I can embed it into Euclidean space by basically taking the square root of this matrix and dividing and multiplying by the inverse of that to all the coordinates, and that kind of embeds it into a space where then the Euclidean distance is kind of, I've warped all the data points, so then this becomes a sphere again after the warping. And so I can do that, or I can just learn this matrix M and then just use this distance instead. Okay, so I'm going to learn this matrix M, which is somehow the best distance for my data. Okay, so in order to learn it, I need some more. I need some more information here. So my input again is going to be this n by d matrix, but I'm also going to have two different subsets. I'm going to have the close pairs, which is going to be a subset of x cross x, and the far pairs, which are, right, so these are pairs of data points that I'm given on input. And I'm saying the close set of data points, I'm going to try and make those close, and the far set of data points, I'm going to try and put those far apart. Okay, so I need to give this extra information, otherwise I have no way of saying which one is better than other ones. Every matrix M is a valid Mahalanobis distance if all of the coefficients are, all of the diagonal elements, for instance, are non-zero. That means that I haven't really lost any information. I've just skewed them. I've just kind of renormalized what the units are. Okay, so I want to say I'm given extra information. I'm given some labels here. So this would be a semi-supervised algorithm. I'm given some labels, but not all the labels. So I'm going to use the rest of the labels, the rest of the data to help me kind of know what the space of the data is. Okay. Okay, so I want to try and come up with, and the goal is some dm or some matrix M in d by d, so that in this Mahalanobis distance that the C are close and F are far. Okay? this is what the goal is going to be. Okay, so this formulation is, there are multiple ways of trying to solve this problem, and there's multiple papers in the literature and techniques, and most of them are, I think, with respect to the techniques we've discussed in this semester, I believe are fairly opaque into what's going on. They set up some optimization problem, and they run some solver on it, and they output some M. And it's not clear what's going on or why this is going to work. So I'm going to describe one that, I'm going to describe a technique from JMLR 2012, which is the top journal of machine learning from Ying and Li. And this is not by any means probably the most famous method here, but I think it's pretty straightforward, and you can implement it with some linear algebra and other kind of first principles from algorithms. So that's why I'm going to describe this one. The other ones are set up as similar, but not quite the same. I have to define, still, I haven't told you exactly what the kind of my numeric goal is going to be. And so I'm going to describe a problem. So M star is now going to be the max M in d by d. So I'm going to find some matrix M where I want to look at the minimum out of all close pairs. Well, this is an arg max. Okay, of this distance xi xj squared. I don't really need the square there. That's the same, but it just makes things easier. Okay, so I want to find I want to look at the, under my distance metric, of all the far points, the points that are supposed to be spread apart, look at the closest pair under whatever distance I've chosen. I want to maximize that. So I want to maximize the closest pair of the far points such that I need to incorporate the close points such that if I look over the sum of the close points, I want to say that this is less than some threshold kappa. Okay, so if I set some parameter here, kappa, I want to say their upper bound on the sum of the square of distances of the close points. I want this to be bounded. I want all the close points, on average, their square distance to be small, and I'll set some constraint. So this will describe a set of feasible M matrices can satisfy this constraint, and I want to find the one that maximizes the closest of the far points. Okay, so this is a modeling choice. I could say I want to maximize the average of the far points while guaranteeing that the largest of the close points is smaller, or something like that. There are other ways to formalize it. This formulation will be consistent with the algorithm I'm going to present. Okay, but hopefully this makes sense as one feasible way of setting up a problem that I can then say, okay, let's find the M that does this, and I somehow want to solve this. Okay, and it turns out the algorithm to try and solve this is going to be fairly, relatively straightforward compared to other ones I've looked at. So does this generally make sense? That's just what the flavor is like. This formulation is not going to matter too much. And in fact, we won't actually use this kappa. This will kind of get buried implicitly inside of some stuff here. Okay, but you want to make the close points small on average, and the far points large in the worst case. Okay? Okay, so let me start writing. So again, like the LDA algorithm, I'm going to need to define some kind of some parts of the solution that you can define. So I'm going to set this matrix H, which is going to be so these are in the close pairs. I want to say xi minus xj, xi minus xj transpose, right? So this is an outer product over all the close pairs. Okay. So it gives me a d by d dimensional matrix. Right, so this is kind of basically, one way of thinking about this is that if I keep the Frobenius norm of this matrix small, I'm keeping the sum of the squared distances small. So basically I want to put a cap on the norm, on the Frobenius norm of this matrix. That'll be roughly equivalent to this property here. Okay, the outer product is kind of like a weird thing that's kind of hard to conceptualize what's going on here, but think of, I want the Frobenius norm of this matrix to be small, and I need this to be full rank. So I need enough close points, at least d, but enough so that they span the full d-dimensional space. Otherwise, I'm going to set h equals h plus delta times the identity. If I add small term on the identity everywhere, that forces it to be full rank, and this is a way of like regularizing the solution, like what we did with ridge regression. Okay, I might decide to do that anyways, where this is some small term here. Okay, so I define this matrix H. Okay, so now I'm going to I'm going to restrict that the trace of M is going to be equal to D. The trace of M is going to be the sum of the eigenvalues of M. So if I look at it, it's just there's other ways to find the trace. The sum of the eigenvalues, for instance, the trace of the identity matrix is D. Okay? So I'm fixing that the trace is D, so this fixes the amount of scaling. So the scaling is basically fixed here. Okay? Okay, and so now right, and I'm going to call this class, this will be a class P of matrices. So basically I'm going to search over the space of M in these class of matrices that have trace P. Okay, so that's just some notation here. Okay, next I need to define some probability, which will be defined over the far points, right? So for each far point, I'm going to give it the ith far pair. I'm going to give a weight alpha I, and it's going to be a probability. So I'm going to have that the sum of these alpha i's is 1, and alpha I is greater or equal than 0. So this is a probability over the far points, and this is going to tell me how I'm going to weight them in some optimization. Basically, I only care about the minimum point, so eventually maybe all the weight goes on the minimum point. But it could be I have like, I'm going to have like 5 points which are equally have the same, or 5 pairs of points that equally have the same minimum distance, so then I would weight them all equally. So this allows me to kind of dynamically adjust the weight on these. Okay, and so now for every pair, I'm going to call pair ij, I'll just say, I'll use tau here. So this is going to be correspond with a far set of points. So then I'm going to define x tau, or x tau ij, is going to be equal to xi minus xj, xi minus xj transpose, right? This is again an outer product, d times d, and then I'm going to transform this using h. So this is going to be Okay, so I'm basically dividing by h. I'm looking at the subspace defined by the close points that I want to maintain small, and basically I'm allowed to move around in kind of a think of this as keeping the directions which are meaningful to keep the small point, the close points close, and I'm kind of dividing through them again. Instead of putting them just on the left side, I'm kind of splitting it. It's full rank and it's square, so I can do this. And then I can split it here and multiply it by this term. So I'm basically normalizing each of the pairs in the far points based on how much I can stretch the close points in a reasonable way. Okay, okay. Now finally I can say that I want to solve for m star equals to arg max of the matrices in P. So this will be the set of these rank, the trace equals D matrices, right? So I'm keeping them so they can't scale too much. And I want to look at the minimum alpha in this probability space. So I'm waiting on the far points. This allows me to have several far pairs which are equally the minimum at the same time. Okay, over all the far points, alpha t, and then, okay, and I'm doing this inner product here. Okay, this is a matrix inner product. This means that I'm, instead of doing a dot product between two vectors, I multiply all the terms together and add them up. I'm doing the same thing with the matrices here. They're now d squared terms, and I multiply the corresponding d squared terms and I add those up. That's what this notation is. But really, if you think about it, and I'm not gonna, I need this form for the actual optimization. But this is basically d of x tau. So this is basically given my choice of matrix M. For the Mahalanobis distance, I define a distance, and I calculate that for one of the far points. Remember, x tau was kind of this outer product, right? It was the outer product of the pair of the far points that I've somehow skewed by h in some way. So h is somehow factored into here, but after normalizing by the close points, then I've got this, I basically compute the distance. So I want to minimize, right, so I want to find the matrix which maximizes the minimum here, and this allows me to share the closest pair across multiple points. Okay, so all this is kind of more in the setup. The algorithm which I'll describe next is not going to be that hard again. Okay, so I can now say, okay, now that I have this set up, you can transform basically this setup into this form here. Okay? Okay, so now that maybe you've, now I can describe the algorithm, which is going to be even, which is not going to be too hard. I need to describe one more thing first, which is a gradient. So I'm going to start with, I'm going to say start with m equals to I, and then I'm going to take some steps of moving m a little bit in some direction. So I'm going to define a gradient on m, and it's going to be parameterized by some sigma. Let's say sigma equals some small value d times 10 to the negative fifth. Okay? So sigma d of m is going to give me a matrix gradient on this, which seems confusing, but I'll just write it down and you'll see it's not too bad. Okay, so it's going to be, it turns out for this formulation, the matrix gradient is going to be a sum over all the far points times e to the power minus divided by sigma. This is just basically some step size effectively in the gradient descent. Okay, so this is the exponent term is a weighting term. I'm multiplying times this outer product matrix for the pair tau that's been normalized by h. And then I just divide through by these weights. Effectively normalized. Okay, so this is the gradient of the matrix. So this is going to be a d by d matrix here. Okay, this is a d by d matrix, and it's going to be fairly small coordinates because sigma will be small. And so it's going to, well, actually that tells me, that's not exactly what sigma is doing in this case. But it's kind of saying, what direction should I move m to decrease this cost function I had before? And it keeps it within the space. I have to keep m within this restricted space. And this gradient will, actually this gradient itself does not keep it in the space, but we'll take care of that otherwise. Yeah. So, okay, so I need to define the gradient. And now I can define what I'll call the Frank-Wolf distance metric learning. It's basically a variant of a Frank-Wolf algorithm, which is kind of a greedy algorithm for trying to find the optimum, kind of like orthogonal matching pursuit was. Okay, but now I want to do it in this context, so step 0. So I want to initialize m as the identity. I could initialize it as something else if I wanted to. And then 4 steps. So steps t equals 1, 2, up to t. I'm going to do the following. I'm going to compute the gradient here, which is d by d matrix. So I want to look at the M matrix I had on the previous step, and I want to compute the gradient. I'm then going to let Vt equals V sigma of, which is going to be the max eigenvector of G. All right, so I'm going to take G, take the maximal eigenvector of G. That's going to be this Vt vector. And then I'm going to update mt is going to be t minus 1 over t mt minus 1 plus 1 over t vt transpose. Okay? And that's it. Okay, and then return this. So I'm going to run this for some number of steps. And this is going to converge to basically the m star, which is what I wanted. Okay, what is this step doing? I'm basically taking a weighted average of the previous answer I had and a rank 1 gradient vector. Okay, so I'm only increasing the rank by 1. The reason this makes it a little bit more stable to do it this way. The nice thing about it is this is going to be a unit vector, which means that this is going to be a unit vector, and I think because this has the right property that keeps that the trace is going to be d. But this is kind of this one was, I'm basically going to take the average over all t of these is what this is doing. This one's getting weight 1 over t, and I have t minus 1 of them that are going to get equally weighted inside of this guy. Okay, so that's what this is doing. And so I'm taking this gradient vector or matrix and taking the top rank 1 direction to move upon, and that's what I'm doing. Okay. So so this is a bit, more of a complicated algorithm that I've described elsewhere in the class and later in the semester as well, maybe with one exception. And so, you know, I didn't necessarily expect you all to understand in the process why I did all these steps and exactly how it works, but I think it's simple enough that you can implement it. Okay, I feel like just about everyone in this class should be able to do the linear algebra in order to, and the programming to pull this off. I have to be able to compute this gradient vector, which is, it looks imposing, but it's, you know, it's made up of simple operations you can put together. And then I have this fairly simple, simple iterative algorithm here. Okay, and I think this goal of distance metric learning is kind of, it's, you know, it's something that often comes up because you're often going to have these vectorized representations of your data without necessarily having the coefficients of the coordinates actually align, or know how to weight two coordinates against each other, or should it actually be kind of a you know, should it actually be the skewed version of this, okay, of this distance which you're learning. And so, you know, there are other formulations and other algorithms which I believe are more complicated. And actually, if you read this paper, you know, my personal belief is the paper, it makes it seem much more complicated than it actually is. But you know, I think this, you know, these are steps that you can do, some linear algebra, and this is a simple iterative algorithm. So this, you could implement this, right? For some of you, I've mentioned you could try and do this as part of your project. And so I know at least one group did it last year and were able to get it to work without too much trouble. So, okay, yeah.
I was just curious, does n, like, is n, excuse me, always going to be like diagonal? Like, are there always going to be like zeros on the upper right side, or is it possible to have like dependencies on other coordinates for your distance?
Yeah, so in this formulation, it's not, right? Kind of what I know is effectively the next simplest version looks at, only tries to solve this version where I'm keeping it a diagonal matrix. That I'm basically just changing the units is what I'm doing here. And so there's a version that is doing that as well. But it's kind of just writing down another formulation, writing a function, and then you run gradient descent kind of blindly on this function. It's a little bit harder to get what's going on. But this one is more general, and I think as easy to implement, if not easier. Again, that other one that does it sets it up slightly differently here. I think it has, I think, a sum and a sum, or something like that, or maybe a sum and a max here instead, right? There are other variants of this. This is just one. The first two algorithms I described, MDS and LDA, those are the kind of the standard way of doing it. There are other variants, but those are by far the most popular. This one is probably not the most popular, but I think is the simplest. Yeah, so cool. So if you have if you don't have any more questions, we'll kind of, oh, great. Oh yeah, so I defined, this is going, I don't know why I use this notation here. I think I just copied, I defined it in the text of my notes, so I copied it up here again. But this is what you will actually need to calculate is the maximum eigenvector of G. So once I have G, which is a matrix, and this actually defines a matrix gradient by itself. I could just move in this direction. It turns out it's better to actually take the top eigenvector of this direction and then take an outer product with this guy to create a rank 1 D by D matrix. Instead of, this is a D by D matrix, but it's going to be probably rank D. The rationale of why you want to do this instead of just move by that, I'm not 100% sure. But this is what the paper proves converges correctly to that under that right problem. And I think it has to do with staying within this restriction that it has to be this trace D matrix. I think that's what's going on, but I don't remember offhand.
Maybe you could introduce more noise too. Or possibly like your whole gradient. Like I'm just thinking,
Yeah.
maybe like stochastic gradients or something, but it might not convert as quickly or something if you don't take the max.
Yeah, I'm thinking what's going on is that if there might be advantage to keeping the rank of M low. Let's say I might only run this for like, let's say D is like 100 and I run it for 10 steps. I'm going to get a reasonable answer and I'm going to get a low rank answer. That means that this would be rank 10. That means I'm getting a 10-dimensional Euclidean subspace actually based on this Mahalanobis distance as well. So that would make it more robust if uppercase T was less than D. So that would be one advantage to doing this. So I guess it's kind of like low rank is a similar way of you get robustness out of sparsity from lasso. This is a way it might be to get robustness out of low rank, a simpler model. You're forcing it to live in the simpler model space. So cool. So then next week, Monday, we'll talk about something leftover stuff about noise in data, and I might talk about, hopefully, how to do matrix completion. I don't have a half lecture plan on that yet, but that's my goal for Monday. Let's see if that happens.